I personally think that modern concrete, I call it concrete composite, uh, can withstand all kinds of pressure. Let's see how it is. Now, concrete is essentially a particulate system with different sizes of aggregate. This is a kind of a model, and binded together by paste. So paste in plastic state, which will solidify later. And this paste could be even mud. So if you look at it a very early age, random rubble masonry of before current era, 2600 to 2000, this is also a kind of a concrete because it's the same particulate material system. So early particulate composite. So these materials, as we know, are weak in tension. You pull, they'll separate out at the boundaries of the larger particles or aggregation of inert material. And you put triaxial pressure, they're very strong. So cement concrete is like that, and you have paste initially plastic, and then when it solidifies, it turns to be something like this. So that's what is cement concrete as we understand, concrete composite. But then cement, quite often we have been using synonymously this word with ordinary Portland cement, invented somewhere around 1824. And at the moment, not exactly absolutely current statistics, but slightly 1 year back or something of that kind. In the world, we use 4 ton per person per year, and India 2 ton per capita per year, because I just calculated it from cement consumption. Cement consumption is very readily available for Indian data, but not as much for concrete. So that's what it is. So you see, every person is using 2 tons per year, and steel on the comparison is 222 kg per person per year in the world. India 87 kg per person per year. About a year or back, that was a statement in Parliament by the minister. So you see, if it was under pressure, the volume that has been, production of concrete or concrete is there, that would have been so high globally or even India-wise. Now, concrete evolved, if I look at it, its technology, which is basically related to not the understanding, but has been used. So ready-mix concrete is something like 1903 patented, and it exponentially grew 2010, and it's still growing. New things will come, and you can see we have 3D printing, modular construction, top-down, smart, intelligent health, etc., etc. That has all come in, and sometimes other physics or something has contributed to this. For example, these 3 gentlemen, their invention of transistor in 1948 in the Bell Laboratories led to high-strength concrete. Silica fume came from there. Okay, so that's what it is. The science of concrete, of course, started around 1920s with Duff Abraham stating strength versus water cement ratio law, and which followed. And today, the science, understanding is improving, and it is quite often might follow the technology part of it. But we don't know actually how it is going to, tomorrow some development in chemistry, nanotechnology, bioscience can actually affect the concrete in a big way, like transistor did. The high strength concrete wouldn't have been there. Reactive powder concrete wouldn't have been there, but for semiconductor. So such things are possible. And now you can design material system for modern concrete. So versatile modern concrete. Dr. Singh was also talking something similar. I have I'm showing 3 components to start with: binder. Then you have got a skeleton matrix, which would be aggregation of inert material, which we call aggregates. Tomorrow it might be even partially reactive or whatever it is. And I list them. 2 of them I am listing, for example, Core 6 or recycled aggregate. And then you have fiber, which is included. It's a part of the material system. So it's part of the concrete composite. For example, polyester fiber, you might Polypropylene fiber you might be using for fire resistance of high strength concrete, steel fiber in pavement, or many other fibers for various, or hybrid fiber system. So that's the three-dimensional matrix where you can represent the concrete, right? And there can be infinite binders. Already he has said infinite number of them is possible. Geopolymer, resin hardener, ordinary Portland cement, water, and silica fume, and so on and so forth. And the fourth dimension is, of course, additives, which has come since 1963 in a big way after the synthetic polymer came into being. And if you see performance, so this performance of versatile concrete, you can have moldability going from zero slump to self-compacting concrete. Any fluidity you can design the system for. Strength, you can go from 5 MPa mass concrete to 200 grades reactive powder concrete. In fact, it's higher, but civil structure 200 RPCs are accepted, because 800 grade have been actually produced reactive powder concrete, which has been used for electronic substrate and all that. And you can have long-term durability performance. You can actually have infinity. Now, one more dimension has come, which is sustainability. So sustainability is very much there. In fact, main contribution to this I'll talk about a little bit later on. Concrete is sustainable, but there are others which actually contribute to. I'll just talk about that later on quickly, since the time frame is less. So we'll try to see how quickly you can finish. So you can design the system depending upon the performance required. So you know what is the performance required, you can design the system. Right? But at the moment, there is a little bit of difficulty, because any design of such system, if the mathematical problem is very well defined, physics is very well understood, then it is pretty easy, like electronics, integrated chips and IC chips and all that. But civil engineering, materials like concrete, which is used by mass, its understanding is also relatively poor, and we use largely natural material. Little bit is processed. So it would take some time. Maybe surrogate model, AI, etc. may help in future. Now, you see, sustainability, if we come at it, we have only one Earth, and we have only one sun, and our population was 1st January something like this. As you can see, very large, and of course the density is shown here, but I'm not really keen on this. And we must balance with the flora and fauna to sustain this globe, the humanity, and all that. So it can be defined in terms of how many Earths do you need. If you need more than one Earth, that means it's not so much sustaining. So biocapacity of the Earth is very important. That's related to the area, right? And useful for that economy yearly. Annually, it may change. It's essentially the area which allows photosynthetic activity and then biomass accumulation, because the sun's energy is only captured by the plants. All right. And ecological footprint is what we need, what we are using, and the area we need for that. So the ratio of ecological footprint by biocapacity is the Earth, number of Earth you need. And ecological footprint of waste is also important here. So resource consumed and yield per hectare. You can take all kinds of resources and all kinds of things that you use. You can put them in same footing, and it can be done. It is done actually. And for waste also, EF comes into picture, ecological footprint. So total area that the Earth has, and ecological footprint is the total area we need for all our whatever we are using, and that gives you the number of Earth you need. So these are expressed in what is called global hectare, and both are used in, and therefore you can actually define sustainability in terms of this. That's what I think. That's the best way. One index, that how many Earths do you need? And it's not my idea, it's already there. Right. So basically, technology that we use, technological process we take from the Mother Earth, and we manipulate, make use, and generate waste. And while taking also we generate waste. And this waste results in actually a kind of additional space you need, right? So that's related to carbon cycle, because there's a natural carbon cycle is there. Plants absorbs and that it converted into decays, maybe your fossil fuel and all that. And then obviously the plant respiration, human respiration generates carbon dioxide. And this carbon dioxide is trapped by the plant itself. So energy and carbon dioxide both are converted and made used into. But then you are having all kind of human generated anthropogenic carbon, and this waste creates a disbalance. Because after last 400 years, the globe, the people, humanity has actually generated a lot of waste by industrialization, everything put together. Construction sector also is there. So we must use them in a most efficient and optimal way, both and consider to construction, and for construction materials should be used, everything should be used, designed and used in an optimal way. So therefore, it's possible to do that. Now, coming back quickly to this, one of the main thing, as we shall see, is main carbon dioxide, which is the major waste and which is creating all kind of problem. You need a lot of plants to absorb that. Sequestration by means, by technological means is yet to come. So cement is one of the major thing which actually contributes only to about 5 to 7%. Largely it is the fossil fuel. But cement also uses fossil fuel. You take that into account, then also it's about 5 to 7% only. And you have infinite number of cements, as I told you. In fact, British code will give you, European code will give you 27 combination. Then there are high halide cement, magnesia cement, alkali activated cement. Geopolymer is one of them, which you are saying. It's actually an alkali activated cement. Calcium sulfur aluminate system, calcium carboaluminate system, cement like LC3, which has been researched quite a bit in this country by my colleague and many colleagues, actually Professor Sasan, and many others. Many other possibilities, there are infinite, as I said. Now, interestingly, the cement industry uses alternative fuel for, quite a great extent. I had the chance a couple of years back to be consultant to Holcim in India, then Holcim. Now, of course, it's all other cement. The factories in Ambujanagar as well as one in Karnataka, the biggest factory of SEC, Wadi. And they have actually put in a lot of things in practice. So all waste they use, obviously their toxicity is tested, and coffee has all this use. So therefore, one component, fossil fuel, they have reduced. They are using grinding aids, overall reduction, technology of the cement is being changed, and they are actually able to reduce the carbon to 0.72 carbon dioxide. This is from NCCBM's report by Dr. Pahuja, and they plan to reduce it to 0.58 carbon dioxide per kg of clinker. But then this clinker, you have other materials, supplementary cementitious materials. So energy efficient system is important, which you was talking about. And embodied energy is the energy that goes during the after construction. So, building materials. And Prakash shows this. So if you see, interestingly, aluminum sheet as the
Sorry
highest.
to interrupt, Mr. Bhattacharya.
Yeah.
Just a gentle reminder that you already crossed 10 minutes.
Okay, I'll take about 2 minutes. Okay, 1 or 2 minutes. So aluminum sheet, if you see, concrete is 200 MPa. If you see, it is only at the bottom. So is there a pressure? I don't think so. So quickly finishing it. So that's what it is. But you are using it in large quantity. So resolved by judicious use. Okay, this I am not coming to because time is not there. So forest is the main important thing. And carbon dioxide is the main issue. And you need number of Earths. At the moment, globe needed 1.75. India possibly needs even more. We have seen, I just did those calculations. So there are possibilities. I'm not coming into all that. Life cycle cost, as you're saying, life cycle carbon you can look into. And last 2 slides I'll quickly go into. For building, energy consumption comes into picture, and number of arts for even structure and building you can calculate. Industrialization of construction is very important. That can reduce of and therefore you can even generate new material like lightweight, high strength ash-treat. We worked on it a little bit. High volume bottom ash cement with PCM blocks, several of those can be worked on. So life cycle cost you can look into, so you can reduce the cost, and that's it. So all performance, you can actually compliance to all performances possible. Thank you.